1, 2, 4, 10. That's all, right? What is SY? 1, 3, 7, 11. And SZ? 1, 5. That's all? Okay. So what will be, so again, so we do one thing at a time. So recall that df plus is nothing but you have to keep computing dfi plus 1, which will be df of s, basically union of all the nodes df, union with previous iteration. Okay. So let's compute the first level. This will be union of df of 1, 2, 4 and 10, which means nothing, 4. So this gives you 10, 11 and 12. Is this clear? I have to compute df of 1, which is nothing, df of 2, nothing, df of 4, 10, 11 and df of 10, which is 12. I have to take union of those df's, so I get 10, 11, 12. Let's try to see what does this mean. df of 4 is 10 and 11, okay. Till before this point, this x equal to x plus 1 is kind of forcing its value. So x will get this value here, whatever value compute here, let's say 26, that will be visible or active here, same will be active here. At this point, x can be either 26 coming from here or some other value coming from here. Okay, that's why 10 is in the dimensions frontier. Similarly, 11, because of either it can come from here or come from some long path here or somewhere. Okay, so dominance frontier is giving you first point where your definition matches its some other friend or cousin. Okay, similarly 12 is in dominance frontier of 10. See, 12 is not in dominance frontier of 4 intuitively, means I don't computation by the, because anyway this x will override it. Okay, so there are other definitions which will come here, but it is in dominance frontier of 10 because this definition, though it is reaching here, it is also going to find some other friend definition somewhere else. Okay. I still not yet. So this is just first level. We have taken only union over all df's. You want iteration, right? Iterated. No, I have not done this part yet. So what I am saying, there are different definitions of x. Because of this definition, I have to insert a phi function in 10, in 11, and because of this definition, I have to insert a phi function in 12. But then now there is a new definition of x in 12. This 12 will start impacting 11, 13 and 14, I think. 11, 13 and 15. The newly inserted definition, because now there is a x equal to phi of xx kind of thing here. Okay, so this will start impacting. Those definition, again we have to look at where all they are going to impact. That is why we are computing this iterated dominance frontier. So now second iteration, I have to compute df of not just 1, 2, 4, 10, but union with previous iteration, that is 10, 11, 12. Okay, I have limited space, but I hope this is clear. First iteration I did df of this. Second iteration 1, 2, 4, 10 union 10, 11, 12. So it became 1, 2, 4, 10. Then 10 is repeated 11, 12. Now its ka df I have to compute. So clearly you know that 10, 11, 12 will anyway come. So you can do some kind of a fast computation. You don't have to again compute this one, you already know. So only 11 and 12 you have to include. df of 11, which is 12, already there. df of 12, 11, 13, 15. Okay, you do it systematically. 1, 2, 4, 10 will give you 10, 11, 12. Then df of 10, 11, 12 will give you additionally 11, 13, 15, 12, all those. The union will be this. Okay. So now I have to go into the next iteration, compute df of So as you can see, mathematical definition is very inefficient. You can implement it very fast. Only compute incremental DFs. Okay, this is more of a theoretical thing, which shows you it is going to terminate after some time and all. Actual computation can be faster. I only need to compute the DF of new things that I have added. I don't have to go back and compute 10 and 12 again. So 13 will give me 15 and 15 will give me nothing. So next time I get back same thing, same set. It won't change anymore. Okay, do it manually if you are not clear. Next iteration, I still get 10, 11, 12, 13, 15, which means I have reached a fixed point. I can't. So what is, so note that I am computing df of this thing. 1, 2, 4, 10, 11, 12, 13, 14, 15, but my answer is just 10, 11, 12, 13, 15. So df plus of x is okay. So which means I have to insert phi of x comma x at 10, 11, 12, 13, 15 in these places. Can you do the same for y and z? So iteration number 1, you will do df of 1, 3, 7, 11. think this will also end here itself. What will be the final thing in Z? So this is my answer. You can, I mean, I could be wrong, okay? I'm doing it informally. Little. So others, anyone who is able to solve this? If you are getting a different answer, let me know. I will double check my answers. Same? Okay. Same not because you copied my. Okay. So if that is same, then I will remove this part. Is it okay? Okay, so final step, we have to now convert this program into SSA form. Now at this point, it would have been good to have some, if I could have I would have been able to write there, it would have saved some time, but let's do this. So one is nothing, all those undefs. I will have to put something because this is my entry node. It contains, oh, I should not put 0 yet. So it contains this undef kind of thing. I'm just putting T here. Okay, so this is implicit. It also says that assume that the entry node contains implicit definitions. Then we have node 2, which only contains x is assigned 2. Again, how visible is it to the last bench people? Okay. So currently I am just copying the graph. Then y equal to 3. So I'm not drawing all the edges because they are going to be the same. Edges do not change in SSS form. So just check, I have put all the boxes and content. Okay, even if it is small, it is the same content as of now, so nothing to worry about yet. Okay. Now how do we start? We have DF plus iterated dominance frontier. So for any definition of a variable, you have to insert a phi function, trivial phi function in the iterated dominance frontier. Okay, so we have to insert phi x in this node, phi for y in these nodes, and phi for z in these nodes. Okay, so maybe I will just do x and y, or even single x is enough, rest is similar. So I will do x only. Actual SSA form can parallelly process all the variables. Okay, so it should not be a very difficult task to mimic that. So let's just focus on df of s. So at 10, 11, 12, 13, 15, I have to insert trivial phi functions. What is a trivial phi function? So x equal to phi of x, where the argument size is same as number of edges coming in. Now typical programs will only have 2 incoming edges, okay, unless you have some complex switch case type of structure in your IR. So in 10, and this is an assignment. (11), 12, 13 and 15. Okay. If you end up getting something in a node which does not have more than one predecessor, then something has gone wrong in your DF plus computation. So all these nodes should have at least 2 incoming edges that you have to verify. Okay. Now how do we start? So let's go back to the algorithm. So rename from the entry node recursively. So let me just erase things which are not very important. I need dominator tree information. I need CFG also, but we can go back and forth there. Right now I don't need those things because I'm not going to attempt SSA for others. So let me just put, even this I don't need anymore. What I will need is a rename stack for X. This will contain current version of X that I am working on. Okay. So we start. So current node that I am processing is 1, which is our entry node. What do? I look at the node. I look for each assignment in this node. Okay. So once again, because I am not looking at Y and Z, why even keep them here? Okay. If it is a non-phi assignment, so it is a non-phi assignment. I picked up node 1, non-phi assignment. I look at right hand side, every usage should be replaced by top of stack, there are no usage. Push mapping X equal to Xi, again something is missing, this is I have created, so initially I will be 0 or 1, whatever you want to start with. So this is my next version that I have to use. So at this stage I have to push mapping X arrow Xi on the rename stack. So I am just going to push 0 here. This says I am going to use X0, okay. If it is YZ, then you might want to keep things, or maybe let me just call it X0. Replace LHS of assignment by X0 and increment your I by 1. What it says is 0 has been consumed now in the version number. Next time you find an assignment, you have to rename it to X1, okay. What do I have to do next? So all assignments have been processed. Same thing you should have done with Y, Z, everything. Now you have reached the end of it. So what you do? You find successors of N. Successors of N, successor always belongs to CFG. So who are the successors of N? Do you remember? Otherwise I have to go back to the image of 1. I have drawn it in a certain ordering. So you know only 2 was the successor of 1. Right? Anyone who forgot that? So in successor of N, I have to rename phi operands through successor injects edge. Clearly this does not have any phi, so I don't have to do anything. Now I have to go to dominator tree and I have to find all child nodes of 1. Okay. I have to recursively do this operation. So from 1 I have moved on to 2. I have still not finished with 1. It is also in some kind of a recursive stack. Okay. Now I pick up 2. They start from second step because that's the recursion. For each assignment X equal to dot dot in N. Again check right hand side. There are nothing in the right hand side. So what is intuitively you have to do? You have to call it X1. Okay. So you push X1 here, you change this to X1. For each child, for each successor, rename phi operations through successor index edge. Again there are no phi operations, so we don't have to do anything. Recursively name all child nodes. So now we have to pick one of these 3, 4, 10, 12, 11, 13, 15. So at this point it does not matter which child node you pick. Only difference it will make is he might get X5 in node 11, you might get X7 in node 11, she might get X12 in node 11, like that. Other than that number, your semantics will remain the same. If you are using X12, wherever X12 is used, if he is using X5, in his program X5 will be used. It will not happen that X5 here and X12 there will mix and match. Okay. So because ordering will make change in the way stack is maintained, nothing else. Okay, so which one should I pick? Yes. Let's take 4. 4. So we pick 4. Okay. Again, we go through each assignment. So only assignment here is x equal to x plus 1. So first we have to look at right hand side. We have to replace right hand side by the current top of the node. So this becomes x1. Okay. Then because there is an assignment, so here also I have to keep incrementing, I keep forgetting this. So I have to push x2 and make it 3. Okay. Now I have to go into dominated nodes, the child. What are child of 4? 7 and 8. So I have done 1, I am in 1, 2, 4. Which one should I pick? 7? Okay. 7 or 8? Odd or even? Let's pick 7. In 7, so currently because we are ignoring y equal to y plus y assignment, this we won't do much. Okay, I am just ignoring it, it's not of interest. So nothing happens, this is a blank. Okay, there is no assignment, so nothing happens. For each successor, okay, so who are the successors of 7? So this step I think I missed for 4 also. Yeah, fortunately we are lucky because there are no x usage in 7 and yeah, successors also the same. So there is nothing here. So 7 successor is only 10. Okay, successor of 7 is 10. So in this successor, I have to change corresponding x to have the correct version number. So this becomes x2. Oh, this has to become x2. Okay. Note that I am changing the right hand side x because it corresponds to the edge which is coming from 7. Not yet popping. I have not popped anything yet. So this phi, which was a trivial phi, now I am changing its corresponding argument. Okay, because if I am coming from this path, x will correspond to x2. So I am fixing that particular argument. So rename phi operands to SUCC edge index. So phi operand, this one, because it's this edge, second edge, I am making it whatever is the current x version at the top of the stack. Okay, that becomes x2. Then I will do it for all the successors. Are there any other successors of 7? This is a problem because I have to keep going back and forth, but 7 has only one successor as 10. Okay. Then I have to recursively rename all child nodes in the dominator tree. But 7 does not have any child node, so this step is done. Now for each assignment for x in 7, I have to pop the stack. But 7 actually did not create any new assignment, so stack is also not popped. At this point 7 process is complete. Okay. So I come back to 4, the same step, recursively rename all child nodes. This is still recursion going on. From 7 I move on to 8. I pick up 8. I have to again check for 8. Let me just check its success. Yeah, it's a blank node. Okay. So for 8, I pick up all the assignment, there is no assignment. I look at successors. Who are the successors of 8? 11 only. Okay, and 11 uses X. So, why did I miss this? No, not this. Okay, so 11 has a, wait. Yes, so 11 has a phi node also. Okay, so I have to rename phi operand. Now which edge it is? I think it is also the right edge. No, this is the left edge. So first operand. Okay, so first operand here becomes x2 because here it is like this and somewhere it comes back. So this also becomes x2. Okay, so this is very important, which operand you are changing. It has to correspond to the edge. And now I am done with 8 also. So this part is done. Recursively rename all child node. Again, no child node of this, no assignment. So I am done with 8. So this was 8 here. I am done. So I come back. There are no assignments, so I don't have anything to pop. So I come to 4. Now that recursion is done. All child nodes of 4 are done. Okay. So I have to now come back to all assignments in X. This is where I pop. See what has happened, this X2, I have taken dominated tree of 4, I have processed everywhere X was used. Now any other X cannot be X2 because that's going from some other path. So X2 work is done now, so at this point I have to pop this. It is removed. Okay, X2 will no longer be used. I will not decrement I because I is giving a fresh version every time. Something is used, it is consumed. I cannot reuse it. Okay, so this is not a stack, this is just a counter incrementing. Stack I have to remove. Okay, so next what do I pick? 4 is done. I am still at 2, so 4 is completed. I have to pick any other kid of 4. Which one should I do? Let's pick up something interesting, maybe 10. 10 is also a child of 2. Okay, so note that again I don't have to go by CFG, I can pick up any child. So let's pick up 10. Why 10? It has a phi assignment, it is a partially fulfilled phi assignment and things like that. And it has another 2 assignments of X. Okay, so 10. So you have to go through each assignment. For this assignment, what will you do? Look at the right hand side. Not exactly, because this is not a non-phi assignment, this is a phi assignment. Okay, so first line of assignment does not apply here. We only have to do this for non-phi assignment. So note that phi assignments get fixed when we come from successor. All non-phi assignments get fixed when we are inside that block. Okay, so that is skipped, but we still have to fix the left hand side. So left hand side, I have to push x3 here, increment this to 4 and make it x3. Okay. So note that again, depending on how you are processing, in which order, you can have an incomplete phi or trivial phi or half trivial phi and still get left hand side version. So it does not matter. These versions can come in any order, but they will be consistent. If I have x2 here, it will be x2 here. If I have x5 here, it will be x5 here. If I have x3 here and there is a use of x, it will become x3 here. Okay, like that. So I am done with this assignment. Next assignment is x equal to z minus 1. So again, it becomes x4. So in a way you can see that this assignment does not mean much because it's not being used. It's kind of a dead assignment, but that's what minimal is. Now x4, I have to look at all the successors. probably 12 is a successor, probably is the first successor, so I will have to fix x4 here and so on. Okay. So I will leave rest of it as an exercise for you to complete it. I know it's a long, it takes time, but if you do it once, it will give you a lot of confidence. It's just mechanical application of your this algorithm. Okay. Come back tomorrow with your final graph with all the assignments in place. Do it for X first. If you have time, if you are interested, do it for Y and Z also. Okay. It will give you a lot of confidence. So finally all of this will get filled, such a big thing. It takes time because this is not really supposed to be done manually. Okay. Any questions? Or you can create, I have actually exercise in which I think I have a smaller. I think in my, okay, no, so this is the only exercise I have. Okay, so any other question? Yes, oops, sorry.
Sir.
Yes.
Sir, why do we have a phi function at block 10 if we are making an assignment to x in the next statement?
We'll come to this point in a few minutes. See, this function depends because there are two definitions of x coming in here. You don't know what is the use. I'm never looking at the usage, right? So suppose this code was x equal to z minus x. Then you were supposed to use x3. Okay, so that x3 has to be computed. So currently we are not looking into liveness of a variable.
Sir, and according to sy we are getting a phi function at block 3 as well.
Phi function at block 3?
For y.
For y, okay, so we'll have to see the code.
But how will we get conflicting definitions of y at block 3?
We have a definition of y at block 3, but see, phi function will become because there will be two definitions of reaching, reaching for y. So we are talking about, okay, so there will be one definition which is undef starting from entry coming here. Okay, there is another definition, this y equal to 3 itself, which will come from this path. Okay.
So but when we loop back from 5, we'll already have y defined as 3.
But that will only be effective on second iteration. What about first iteration? Suppose I have a print y before y equal to 3. Suppose my program is like this. Y equal to 5, print y equal to 2. It's in a loop. Okay. So are you saying the value of y at the start will always be 2? No, there are two different definitions, 5 and 2. First iteration it will be 5, all other iterations it will be 2. So how will you capture it in SSA form? So first time you have to pick up outside definition, next time you have to pick up in the, so two different definitions are reaching. So you have to insert 5.
So but why are we considering the undefined definition from the entry point?
Why are we considering undef? Okay, so let's say this is not here. What will your program print in the first iteration? No, that's the thing. Garbage because of why? Which language are you talking about? Fortran, old Fortran, if you have a capital letter, it is always assumed integer, it is assumed to be defined. So it will probably print 0. Okay, there are many languages where you don't have to define or declare a variable before use. The first time you use it, it gets a value 0. Secondly, you might want to have, and this is more like a, if you want in your language, let's say undefined variables are not allowed, then first thing you can assume that such a thing is an error, you should not have, never be getting it. Okay, or in that case, you don't need to have undef in the entry. So this is some way, most general way of describing SSA. Okay. So when you read the paper, there are one or two more things which I have skipped here. So they also introduce always an entry block, exit block, and an edge from direct edge from entry to exit for some technical reason, which I don't want to confuse you, because most of the things are here, the crux of the material. Okay. So anything else? So yes, so when you are designing an analysis, one thing you have to very carefully read is the semantics of your language. Analysis, same analysis may work for C but not for C++ or Java or Python, because their meanings of certain constructs are different. Morning also we talk constant propagation. Generally you will never see constant propagation on floating point variables. Why? Because floating points are not exact. So if you do something at compile time, and somebody was talking about cross compiler, so maybe you are compiling on a 16-bit architecture for generating code for 32-bit architecture, their floating point representation could be different, their precision could be different. So if you replace something at compile time, it might give you a different answer at runtime. Okay, so these kind of trade-offs, these kind of issues you have to remember. Typically your books will talk about analysis in a most general setting, infinitely precise floating point or infinite width integer. But again, if you are doing computation or compilation on a 32-bit machine for a 64-bit machine, even integer folding might be an issue. At runtime you might get a bigger integer than what your compiler can support. So in such cases you should not try certain optimizations. Okay. So let's continue with some more properties of SSA. So one is we'll talk certain features. Secondly, I mean SSA form, as we saw, is not an executable format, so we have to finally execute the program in real situations, so we have to convert it to executable, and what challenges does it produce, and finally how SSA is useful in certain optimizations. Okay. So one thing, whenever you are doing an analysis, it's always advisable that your analysis should be fast enough. Okay, it should be faster than, when you do some analysis, it should not be so slow that your optimized program does not give you any benefit. If it takes 2 days to analyze a program which you are going to run only 2-3 times, there is no point in doing such an analysis. So SSA construction, if you do real worst case analysis, it is a cubic algorithm, cubic in maximum of number of nodes, edges, number of assignments, and number of usage, basically definitions and usage. So you take worst case of all these 4 quantities, it's cubic in that, which seems it's very bad. Generally you want linear or at most square quadratic complexity, but these worst cases, okay, computation of DF or R square, these worst cases occur very infrequently because you don't have assignment in all nodes, you don't have a usage in all node for every variable. Okay, so practical complexity is actually linear. In almost all programs you can get linear complexity. I keep forgetting. In fact, you have a linear time algorithm for placement of 5 functions. This was given again another interesting classic paper using a new data structure. So you can see your algorithms or data structure course can be useful in compiler. Okay. So as I talked about it, the typical definition of DF is very It's very inefficient because every time you have to compute DF of all the nodes, but you can do an incremental analysis. Similar thing happens here. Okay. Now let's talk about SSA form, because again, good thing that somebody asked this question. So SSA forms, for very simple program, I will give you illustrations. So here is an original program. Okay. Actual values are not interesting. So what will be the SSA form for this program? Can you just draw it intuitively? I mean, only place where you will introduce 5 function is last set, last node. So what you will do most probably will be what we have done till now. It will give you minimal SSA form. So why is it called minimal? Because you don't introduce 5 functions at all joint node. One of the simplest thing is introduce 5 at all the nodes, all the joint nodes. Okay, but it does not do that. It only does it where two different definitions are meeting. Okay, but even that is not optimal, like we saw in this case. This 5 is really not needed. Okay, because this is never going to be used. So let's see what we can do. So have you got it? It's not very difficult. So here is a corresponding minimal SSA form. If you apply your algorithm, you are going to get same except the numbers. Okay. What do you see here? Again, what is your observation about those 5 functions? Suppose this is a complete program. So x3 and y3 are never used. We don't really need them. So you can do a separate pass of dead code elimination, that is one way, but why even insert them if they are not required? So somebody proposed this. Okay. So somebody proposed what is called pruned SSA form, and then they found out that okay, pruned SSA form is kind of as complicated as doing a separate analysis of dead code elimination. So they introduced semi-pruned. I will explain them. So pruned SSA is exactly what we want to do. Really we want to achieve only 5 functions where they are live. Okay, even if 2 definitions are reaching, if they are not useful, then we don't want them. So this inserts fewer 5 functions, but it costs more because you need to do extra analysis. Okay, so this requires what dead code analysis or live variable analysis. I am keeping them almost similar. Okay, but the thing is, if you remember morning I said SSA is useful because it allows you to find definitions and usages quickly. Now to introduce SSA, if you have to do live variable analysis, then what is the point? If you are doing live variable analysis anyway, then introducing SSA form may not serve that much purpose. Okay, so that's the challenge with pruned SSA. But suppose you are able to do pruned SSA, this will how it will look like. You only insert 5 for Z. Okay. Other way to achieve it is you do SSA and then do a dead code elimination pass, which is easier, slightly easier. Okay. But can we do something in between? Not introduce, at least try to avoid certain 5 functions. So some semi-pruned does that. It discards those names which are used only inside a single block, which are not going beyond a single block. So if we look at here, if you see x1 and x2, the definition and usage are restricted to a single block. Y is used across blocks. Okay. So you don't need to do a very complex analysis to figure this fact out, whether a use of a variable, is it coming from a definition in the same block or from outside. You are not interested in actual definition, you are only interested in whether it is local or outside, that's all. This can be done very quickly. So what you do is you discard those names which are local, because if you know that X is being defined and used in the same block, then you don't need it anywhere else. Okay, so the total 5 functions that you will insert will be between minimal and pruned. Okay, so it only needs local live information which is easy to compute while you are parsing your code. So this is how your semi-pruned program will look like. So as you can see, we are able to discard certain 5 functions, but we have to keep certain others. Okay, y is live outside block, x is in live only inside block. So how do you do this liveness analysis? It's very easy, as I said. Though I am showing it as a separate pass, it can be done along with your parsing, okay, or while you are constructing your 3 address code. So given a block, you start with a defined set which is empty. You see an assignment v equal to x of y. Again, this is a generic thing, you might have to adjust it to the kind of assignments you have. You see a usage x and y. Okay. Now, if x is already part of your defined set, if it is not part of defined set, which is definitions coming from somewhere outside, so you add it to non-locals. I think there is to be a non-locals global variable called non-locals. And if y is not in defined, then you add it to non-locals and you add v to defined. That's all you have to do. So only a single pass over the block is sufficient to classify every variable as local or non-local and every definition as defined, every variable which is defined to collect that. Okay. So with this, whatever is in non-locals, you have to keep their 5 functions. If there is something local, I mean something is not part of non-local, you can ignore them. Okay. So all this is good, but at some point we need executable code. What do? We have to fix up these 5 functions. Okay. So how do we do it? Basically you insert, again something Lokanand, right, you suggested in the morning. Insert copies in the predecessors to mimic 5 function. It's a very simple algorithm, but like every simple thing, there are cases where it will not work. Can you imagine why it will not work? It looks so simple. So again, it will work if you are not really interested in optimizations. If you are just interested in converting to SSA and removing 5 functions, it will work. But that's not the goal of our whole purpose of doing SSA is do optimizations. Okay. So the moment you introduce optimizations, certain things happen which will cause problem. So let's see why. The other challenge is it might end up adding lot of copies, but that is again something which can be handled by compiler by optimizing those assignments in the later passes. So you have register allocation pass, which is a very, very important concept in compiler. I think Professor Manas will cover it in later part of this course. Register allocation, it decides which variable go into register and which do not. It tries to optimize assignments by just reassigning registers and so on. Okay. So here is a phi removal example. So I have a SSA based program, x0, x1 and x2 is phi of x0, x1 and then I am using x2. So how do we remove it? As I said, across each edge you back propagate an assignment to appropriate argument. So this will become your non-SSA SSA'd program or non-SSA'd SSA program, right? And as you see, this is going to be correct. It's no longer SSA, but it is now an executable. You can convert it into machine code and execute it, right? So what is the challenge? First challenge is lost copy problem. Okay, so here is a program. Please convert it to SSA using whatever method you want. Yes? And let's say if this program executes 2 iterations of for loop or whatever loop, 2 times it goes over that loop back edge, what will be the output? So basically what will it print? If that edge is taken twice, let's say your loop executes twice. So x is 1, y becomes 1, x becomes 2. First time you come back, y becomes 2, x becomes 3. You come back, y becomes 3, x becomes 4. Then you come out, print y. So you are printing 3. First time 2, second time 3, and then you will print it. Okay. So are you able to convert it to SSA? The only variable which is problematic is X. So first do it, that is actually with some optimization. Please check if you have similar program or if there is any mistake. So again, if you execute this program, x1 is 1, you come here, x2 will pick up x1 because we are coming from left edge, this will be 1, so y will be 1, x3 will become 2, you come back, this time x2 will pick up x3 which is 2, so y becomes 2 and then x3 becomes 3, again x2 will become 3, y will become 3, x3 will become 4, but then we exit, so we will print y which is 3. So all good? Okay. So there is an optimization called copy propagation, something like constant propagation. What it does is, if I have a chain of copies, just copies, x equal to y, then z equal to x, then w equal to z, I can, what can I do? I can say x equal to y, z equal to y, w equal to y. So what it does? It will delete lot of assignments in between. So I don't need x equal to y probably, I don't need z equal to y probably, because only z is getting printed. So I do the same operation, same optimization here. Okay. So if there is a chain of assignments, I can replace things. So how do I do that? What copy propagation I can do? So this should be the final thing in some sense. So see, y is assigned x2 and later I am printing y. So I can replace this by x2. There is no point in keeping y. The moment I do that, I don't need y anymore. I can remove it. Okay. So now my program is x2 is phi of x1 x3 and x3 is x2 plus 1. I did exactly what copy propagation says. Okay. Can you execute this program? It's not different from constant propagation. In constant we are replacing variable by constant, here by another copy. Only thing is, yeah, here it is a variable. So program is same. Can you execute this program? x1 is 1, we came here, we picked up left hand side, so x2 is 1, x3 is x2 plus 1, it is 2, we go around once. x2 is, now we will pick up x3 which is 2, so x2 is 2, x3 is 3, we come across here, so wait a minute, it should be x1 comma x3, yes, so okay, this is fine, yes, SSA is still fine. Now you do what? You have to convert it into executable, I forgot that part, okay. So how do you convert it into executable? You move assignment on the corresponding edges, right? So then you have to move x2 equal to x1 here, right? That's how we do it. And you have to move x1 equal to x2 equal to x3 here on this edge. Now this phi can be removed. Now you execute this program. So after phi removal, this is how your program will look like. Now answer will be, output will be 4. In fact, it is not very difficult to see what has happened due to phi removal. We were assigning x2 first, then x3. And as I said, there is no ordering between phi's themselves, but there is an ordering between normal statement and phi. Phi has to be the first statement. Okay, so this is the first statement, this is second statement. Phi removal, it has swapped. Okay, so anyway you can see, even if you don't want to execute, something as bad has happened. x2 should have been assigned before x3. Now x2 is getting assigned after x3. What happened here? Where did we go wrong? We followed the rules. Okay, that much I can guarantee you, even if you might have missed something. Can you see what went wrong? Semantically. It is? It's not, basically that's the goal, right? We have to come out of SSA. And we did that copy back argument wise. See, this edge, it's actually a time travel edge in some sense. From iteration 2 it is taking you to iteration 3. But when you are moving things back, something which is happening in iteration 3, you have moved it back to iteration 2. Okay. However, this thing is not captured by your static graph. In static graph, both these statements still remain in iteration 3. So this statement is actually iteration 2, this is iteration 3. But the way your program is, it cannot be captured. This edge really cannot capture the time travel, okay, or iteration, across iteration travel, cross iteration. So these kind of edges are always trouble. If you are moving code, morning also you were saying move our code, these kind of challenges, anytime you are touching code and moving it around, be always careful about such edges. There is a special name for such edges, generally they are called either back edges or cross edges, okay, because they will always mess up your execution. As long as you are handling them properly, then your movement of code is fine. So there is a problem. From here to here, actually you are changing your time frame, your timeline. Okay, so this is really a bad thing to do. So what can we do then? Oh, okay, execute this loop 3 times or 2 times and execute this loop 2 times. What is the output? So x1 is 1, x2 is 1, x3 is 2. First time. Now x2 is 2, x3 is 3. Once again, x2 is 3, x3 is 4, we come out, answer is 3. Do the same here. x1 is 1, x2 is 1, x3 is 2, x2 is 2. Go along once, x2 is 3, x2 is 3, go along twice, x3 is 4, x2 is 4, you print, answer is 4. So two rotations across that loop. Once in original program answer is 3, in your new program answer is 4. Do it, okay? And the exact reason is now x2 is happening after x3 has been updated. Okay, so is there a way to fix it? So once again, I mean for you it's kind of, we have not discussed it any time, but there is a very standard solution to such cases, such things. Swap again. No, but then you might end up swapping before and after. It has to be done only on certain edges. Okay, so this thing is, this is called edge splitting. This edge is time traveling, you introduce a stop in between. Basically this point and this point are not really in the same iteration space. So you have to create a break in between. So introducing a edge split, I don't know if I have it in, yeah, solution is this. So your x2 equal to x3 should be on a separate, again this is time traveling, so in between you have to have a stop. Okay, now this program will work correctly. And this is a standard solution. Anytime you have a loop and you are moving code around, just check whether that movement is going across iteration. If so, you have to introduce a block, you have to split the edge. Okay. Other one is, this is always work, this is specific to the particular case we have. Okay. Now there is another very interesting problem. Swap problem. Oh, okay, yeah. So please convert this program into SSA. And once again, what will be printed by this program if you go over it once, go over the loop once? So you can see we are just iterating or implementing swap in the middle block. That's a standard way of swapping two variables in a C-like language. X equal to t or t equal to x, x equal to y, y equal to t. Right? So what will be printed? So if you go over it without loop, it will print 1. If you go over once, then it will print 2. So basically, depending on how many iterations, odd iterations it will print 1, even iterations it will print 2, something like that. Okay. Now convert it to SSA. Please check, this is the program you are getting. Is it correct? Converting that program into SSA form. Right? Once again, I see lot of assignments here, just variable assignments. So I can do copy propagation. Okay, and SSA form makes it easy because again, as I said, for every use there is a single definition. So I am using, these are copies. So X is same as A2 and later X is used. So I can simply replace it by A2. Why do I need it? So I can delete it. So now I see A3 is B2, B3 is A2, all those things. Okay, anything else? Okay, yeah. Oh, this A3 is defined here, it's used here. Okay, so why not replace this by B2? So now there is no use of A3. This B3 is defined here, used here and here. Okay, value is A2, so why not change it to A2? Then I can get rid of B3. Okay, this is what I will get after I do copy propagation. I think somewhere. Yeah, so A2 is A1 B2, B2 is B1 B1, it should have been B1, right? B1 A2 and then I am printing A2. Okay. What is the problem? So first time A2 will be A1, so A2 will be 1, B2 will be 2 and I will be printing 1. Okay. What happens second time? A2 will become 2 or and B2 will become 1. So if I print, this will be 2. So everything perfect. Now you do conversion out of SSA. So conversion out of SSA. So you'll have to insert A2 equal to B2 and B2 equal to A2 here and A2 equal to A1 and B2 equal to B1 here. And then 5s will be gone. Okay. Now what happens? Now execute this program. It's written much clearly there. It's the same. So A2 is 1, B2 is 2. Then A2 becomes 2, B2 becomes 2. So both A and B are 2 and you will always print 2. It does not matter how many times you go over the loop. And it's very, again, see, intuitively it's so simple. Here we are swapping using a temporary. There we are trying to swap without a temporary. Okay. And in this case, even edge splitting is not going to help. What went wrong? Up to this point, things were fine. From this point to this point, something went wrong. Some assumption we broke. So last time that assumption was the two sides of looping edge are kind of same iteration, defining the same iteration, which is wrong. They define two different iterations. So is there any difference between this block and this block? Something I said, some property. Next word I say, I think you will remember. Some property of phi functions. Something you do in Python but you cannot do in C. Or something. Concurrent assignment. If I write here A2 comma B2 equal to B2 comma A2, this will work fine. Okay. The reason is these two assignments are considered to be executing concurrently. But when we tried to convert it out of SSA, we have introduced sequence. There is not deadlock. We have introduced sequencing. First A2 happens, then B2 happens, which is wrong, which is not correct here. Here A2 and B2 are happening concurrently. That's the assumption of phi functions. Instead, as I said, you write in Python A2 comma B2 equal to B2 comma A2. This is a correct out of SSA execution. Okay. This problem is coming again because you are unnecessarily introducing dependency between two phi functions. You are saying this phi function executes after this phi function, which is not the correct semantics. Okay, when you are converting into out of SSA. So how do you fix it? Now one is, yes, use Python kind of semantics. If there are concurrent phis, you introduce concurrent assignment. This has to be A2 comma B2 equal to A1 comma B1. This will be A2 comma B2 equal to B2 comma A2. That is one way, but maybe your language does not support it. What do you do? In such cases, you have to check for dependencies, textual dependency among phi functions. A1, so B2 is defined, used here, defined here, A2 is used, defined here, used here. So even though technically phi functions don't have a dependency, because of the way we have written them, we have introduced a dependency. So if you are going out of SSA, you have to break this cycle by putting temporaries in between. Okay. So this is, I don't show, but finally you will end up getting same kind of program. Okay. So you have to worry about such cases when you are coming out of SSA. Okay. So this fix requires compiler to detect and break dependencies from output of one phi function to input of other phi function. Because the moment you say this is output and this is going into input, mentally you are introducing a dependency. Okay. All right. So now let's come back to the reason why we went inside SSA. Any questions in between? Okay. The thing is, why that is important? People have figured out solutions and everything, but you have to know it, because again tomorrow you will introduce a new optimization and end up facing some similar issue. So you should be able to detect why it is happening. What assumptions am I violating? Okay. And that's the thing, you have to read assumptions very, very carefully, very critically. Yes. Okay. So are you saying in the generated code or where? In the intermediate phase?
Because we have to, for every new assignment, we have to create a new variable.
Yes.
We have to reference to a new location.
Right, but again, see, look at this. Okay, so these analyses happen function by function. They are not inter-procedural typically. SSA form is within a function. So at a given time, you have a very small program in your memory. Okay. Secondly, this is again compile time, one time thing, but the optimization you can do, the speed of the optimization compensates for the extra memory that you are using. Even you do extra analysis, that all is compensated because the benefits you get. Okay. So one thing we saw in the morning was constant propagation. I think depending on time, we will do it today or tomorrow. Now we have a tea break again or something at 3:30. Okay. So I'll just finish this slide. Dead code elimination becomes easy. I've shown you some snippets. You just have to see whether x1 equal to something is there. Is x1 used anywhere or not? You don't have to do any more data flow analysis. It's right there. Okay. There is a concept called value numbering. Again, it's outdated, so we won't do it anymore. There is a very nice optimization, which in itself is so powerful that you can do different optimizations by doing some one analysis. It's called partial redundancy elimination. Okay, so that is also possible using SSA, and we might do it. Loop invariant code motion. If inside a loop you are assigning x equal to 5, you are unnecessarily executing it again and again. Okay, it may not be written as explicitly, but such code can be moved out of loop. Strength reduction. So you replace strong operator which takes longer cycles, like multiply by 2 you can replace by bit shifts, which is much cheaper operation in machine, or exponentiation can you replace by again bit shift or multiplication. Okay. So all this can be done using SSA easily. Why is right? So one of them we will see is this conditional constant propagation after we come back from our break. Okay. Yes. Thank you. Any questions? Quick. So we look at one example of one optimization which is done much better. Constant propagation we saw in the morning. Now we will see how we can do it better using SSA. Okay. Thank you.